Hey everyone, welcome back. Let's go on and start to get into some of these reactions of carbonyl groups that are found in aldehydes and ketones. Now, I'll admit I'm kind of going out of order from the chapter, only because I think, rightly or wrongly, but I think that I can present things in an order that's a little bit more logical. So we'll see what you think. At least I hope that this works. So we've already covered about the carbonyl group in general, that it has an electrophilic carbon atom, and that we must therefore expect that nucleophiles will attack this carbon atom. And I think the easiest and most straightforward way to present the material is for me to show you how these reactions work, maybe not focusing on arrow pushing, but I think I can at least show you how the reactions work step by step, and so what all of the intermediates are. This is also a good time here at first to showcase the difference between reactions that occur in an acidic medium and reactions that occur in an alkaline medium, and we will come across both for the rest of the semester. And so I want to show you how, first of all, you can tell what's going on. Are you an acidic solution or alkaline solution? And the answer to how you can tell that is by looking at what you're given. Here, for instance, we're given, again, acetophenone. I could have used any other aldehyde or ketone. And we're told that it's reacting with dilute aqueous acid, H3O+. That tips us off that we're in an acidic medium. So if you see any kind of strong acid mentioned, H3O+, or it might say H2O and H2SO4, or it might say H2O and HCl, something like that. Anytime you see that you've got strong acid present, that tells us that we need to be careful in discussing the reaction, that we don't use any strongly basic anions, because those can't exist in an acidic medium. And likewise, in an alkaline solution, for example, here, we're told that there's the hydroxide ion in water. And this might say NaOH in water, it might say KOH in water, any strong base like that. And of course, in an aqueous system, the only base you can really have is the hydroxide ion, it's the conjugate base of water. And so that tips us off that we're in an alkaline medium. And what that tells us is that we need to avoid any cations. We don't want to see any carbocations, so no carbons, no oxygens with a plus charge on them, nothing like that. The only cations that can exist in alkaline solution would be metal cations. So Na+, K+, right, Ca2+, things like that can exist in alkaline solution. And just as in acidic solution, we turn that idea on its head. And in acidic solution, we don't want to see any strongly basic anions, no OH-, no alkoxides like CH3O-, certainly no carbanions, nothing like NH2-, which is the conjugate base of ammonia, an exceedingly strong base. Those things don't make sense in an acidic solution, right? They're too strongly alkaline. So we can't use those. We can't use structures like that when we're analyzing a reaction that occurs in an acidic medium. And so that's the way we're going to approach it. And the reaction I would like to present first, and again, I'm going a little bit out of order in your book because I think it will pay off in the end. The reaction I want to talk about first is hydration of aldehydes and ketones. Now, this reaction is the exact opposite of useful. This is not anything that's ever used industrially or synthetically. But the reason your book, just like every other organic chemistry book I've ever seen, brings it up is because I think it's illustrative in helping us understand, first of all, what we said a moment ago about reactions in acidic versus alkaline medium, and second of all, illustrative of other reactions such as the formation of acetals and hemiacetals. So that's why we're going to do it. But this is not a reaction that's ever going to be used in industry to make something else. In fact, quite the opposite. Because what we find with really all ketones and aldehydes, again, here I'm just using acetophenone as an example. I could have used any other ketone or aldehyde in this, and the exact same reaction would happen. Well, in most places for much of the year, there's a certain percentage of water vapor in air. And so what this means is that although all these steps are reversible, meaning that you could also go from this backwards step by step to the starting material, there's always going to be some degree to which water will add to the carbonyl carbon, whether in alkaline solution or in acidic solution. One way or another, that oxygen atom is going to act as a nucleophile and create what we could call the ketone or aldehyde hydrate. And this is a problem because in most cases, we need our reagents to be scrupulously dry. And so that's why most ketones and aldehydes, if there's a stock sample in the stockroom, for instance, it's not rare that we will keep some drying agent in the bottle to suck up any water so that we don't get any of this hydrate, because this is going to react very differently and quite possibly not at all as compared to the original aldehyde or ketone. Nevertheless, it's, I think, a good idea to spend just a few moments on this reaction, just so that we can understand the process of nucleophiles adding to carbonyl carbons, and also the differences between acidic medium reactions and alkaline medium reactions. So, in the case of if we were to dissolve some acetophenone in dilute aqueous acid, the first thing that will happen is going to be that we will protonate the carbonyl oxygen. And that's very common for reactions that occur in acidic solution. Here we happen to have water around, so there's going to be some of its conjugate acid, hydronium, that's around. And that's what will put the proton onto the oxygen. And again, we could draw the mechanism, but I think it makes perfectly good sense even without the mechanism. So let's try going this way. Once we've put the proton on that oxygen, that now makes this electrophilic carbon atom even more electrophilic, because now this oxygen has a full plus charge on it. And so this species is really going to want attack from a nucleophile in order to get rid of the plus charge on this oxygen. And that's exactly what will happen. A water molecule will attack that carbonyl carbon and form a bond to that carbon, as you can see over here. And in so doing, we will also break the carbon-oxygen pi bond. If we didn't, then carbon would have 5 bonds around it, and that's no good. But in so doing, we get rid of the plus charge on this oxygen. And we now have an sp3 hybridized carbon atom instead of sp2. So that's the next intermediate. And then all that we need is to pull a proton off of this oxygen to give us our neutral product. Remember, you always want to aim for a neutral organic product. And in fact, will be a water molecule that will do that for us. And so then you get your hydrate over here. And again, these steps are reversible. You could, in principle, follow the exact process, except exactly backwards, and lose a molecule of water and go back to the ketone or aldehyde. But so there's going to be a rapid equilibrium here. But there's always going to be some of both species present, unless, as I said, we're very careful about scrupulously avoiding water with a drying agent or something like that. So this compound is now pretty much dead in terms of usefulness. And so that's why normally we're very careful to dry our ketones and aldehydes very thoroughly to make sure there's none of this unreactive hydrate. What would that look like in alkaline medium? Well, one thing I've noticed over the years is that if there's reactions that occur in both acidic and alkaline medium, and not all of them do, by the way, there are going to be some that we'll learn that will occur only in basic solution, and some that we'll learn that will occur only in acidic solution. And I think there's always going to be a pretty good reason as to why that is. So in any case, one thing I've noticed over the years is that reactions that can occur in alkaline medium as well as in acidic medium, I find the alkaline medium reaction simpler. It is fewer steps. So we'll see what you think. In the case of if we were to dissolve our acetophenone or whatever other aldehyde or ketone in aqueous hydroxide solution, now we don't have to worry about protonating the oxygen first. In fact, we'd better not, because if we did, we would have an oxygen with a plus charge, and that's no good in alkaline medium, right? So we won't do that. Just as careful as we were to do that in acidic medium first, we will be as careful not to do that in alkaline medium first. And whereas a water molecule attacked our carbonyl carbon in acidic medium, now we have a much better nucleophile, namely hydroxide. Recall in chapter 6 that one of the things we said that other things being equal, anions make better nucleophiles than neutral molecules. And here other things are equal. Hydroxide ion and water are conjugates of the other. Water is the conjugate acid, hydroxide is the conjugate base. So the anion is going to be a much better nucleophile here. And so that will just attack our carbonyl carbon directly, forming a bond to it as you see here, breaking again the carbon-oxygen pi bond, and leaving a minus charge on this oxygen. And that minus charge is perfectly fine in an alkaline solution. We needed to avoid that in acidic solution. That was another reason why we protonated the carbonyl oxygen first. But in alkaline medium, no problem. You can have alkoxide ions like that. Anyway, now all we need to do is, to get to our neutral product, is protonate that oxygen, and that will get rid of the minus charge. And we've got water around that can do that for us. So water will give a proton, put the proton on that oxygen, and we will get the same neutral compound. So, like I said, this is not a useful reaction, quite the opposite. But it does give some idea as to how to think about reactions in acidic solution and how to think about reactions in alkaline solution. One other rather similar reaction generates what's called cyanohydrins. And cyanohydrins are species that look like this. I'll say a cyanohydrin. They're species that have a nitrile functional group and an alcohol functional group on the same carbon atom. Compounds like that are called cyanohydrins. And they're actually quite useful. There's things that you can do with that nitrile functional group afterwards. Remembering again, don't forget that the nitrile functional group is C triple bond N, right? So the cyanide ion is Cn minus with the triple bond and the minus charge in carbon. So if you need to review those structures, please do so. This reaction is generally done under alkaline conditions. And so under alkaline conditions, the hydroxide will deprotonate some of the HCN that's in there. We got a solution of HCN, hydrogen cyanide, and aqueous base. And the base will deprotonate some of those HCN molecules. And then you'll get the cyanide ion, which will attack that carbonyl carbon directly again, just like happened with hydroxide ion back here with hydration in alkaline medium. Only you will get a stronger bond between two carbon atoms than between an oxygen and a carbon. And also the other reason that we get cyanide ion adding here rather than OH minus is that there's a lot more hydrogen cyanide around. In general, I think we'll find that the hydroxide ion is catalytic. So that's why the cyanide ion attacks here. Once again, we get this oxyanion, and all we need to do once again is to pull off a proton. And I could see that proton coming from either a water molecule or an HCN molecule. I'm sure both would happen in real life. So whichever way you choose to think about it, this alkoxide intermediate will take a proton off of either water or HCN and give you your neutral cyanohydrin. And actually, I am rather tempted to stop right there for now. I think it's better for a video to be too short than for it to be too long. I'd kind of like to deal with acetals and hemiacetals separately. So we'll see you next time in that video. Have a good day.